Hi everyone, welcome to our last video for week 4 on confidence intervals for a proportion. One of the most common types of confidence intervals is one that involves proportions. So this is one of the most common things we're trying to estimate. A proportion represents a part of a whole. So we're looking at a part of a larger population that has a characteristic of interest, and we can represent that part of a whole as a fraction, decimal, or percentage. And the decimal, we've already seen, is the most common way to express that. Proportions can also represent probabilities. We've seen that before in previous weeks. Proportions can be obtained from samples and population. And we're going to be using sample data to find confidence intervals to estimate a population proportion. And just like the confidence intervals for means, that interval estimate is going to be centered around this sample proportion. And that interval will then estimate the population equivalent. So we have, sorry that my little clickies are out of order. We have some notation for proportions. Lowercase p is the population proportion that we're trying to estimate. And p prime is the sample proportion. Sometimes you'll also see another notation used for sample proportion. This is very book specific. Sometimes you'll see p with a little hat over it, red p hat, which is also the sample proportion. So p prime and p hat both mean the same thing. They're both sample values, sample statistics. That p prime, that sample proportion, is the number of sample subjects with the characteristic of interest divided by the sample size. And that will be a decimal value. And q prime is the proportion of the sample that does not have the characteristic of interest. So q prime is the complement of p prime. You can calculate it as n minus x divided by n, or just 1 minus p prime. You will very rarely need to worry about q prime, as most of what we're doing, the calculator is going to calculate it in the background based on that p prime or x value that you feed the calculator. We have assumptions for this confidence interval, just like we did for the other types. We are assuming again that the sample is a random sample and that the conditions for a binomial experiment are satisfied. If that n, x, and p symbol looks familiar, that's because we used it about 2 weeks ago when we talked about discrete probability distribution. We are using a normal curve to estimate something that is inherently binomial. You either have the characteristic of interest or you don't. And so we need to check that the conditions for a binomial experiment are satisfied. It is safe for you to assume they have been met when you're reading problems in a book, but again, as a researcher, you should check these 4 things: fixed number of trials, 2 outcomes for each trial, outcome of each trial is independent, and the probability of success is the same for each trial. In addition to this, the previous slide, we're assuming those things are true. For proportion, you can only construct a confidence interval if the sample size times the proportion is greater than or equal to 5, and the sample size times the complement is greater than or equal to 5. If both of these things are not true, the normal estimate or the normal approximation of the binomial distribution is not going to be very good. So you need to check these conditions before constructing your confidence interval, even for problems in the book. So check these before you start, If they are not met, if either one of these conditions fails, don't construct the CI. You would simply say n times q prime is less than 5. I can't do that. And you would move on to the next problem, and that's okay. So this is very important. When you're doing confidence intervals for proportions, you have to check these two conditions. N times p prime is greater than or equal to 5, and n times q prime is greater than or equal to 5. That limit of 5 is somewhat arbitrary. Most of the books that colleges use is 5, but I also teach AP stats at the high school level, and they assume 10. Their requirements are even more stringent. So work with 5, but notice if you see another textbook that this number is a little bit different, it just means they want to be even more sure that the normal distribution is an appropriate approximation for the binomial distribution that they're looking at. So for finding it by hand, we're going to start by finding or calculating p prime, q prime, and the sample size. We're then going to find a z-score that corresponds to our confidence level. So we're back to inverse normal table E, standard normal approximation. We're then going to calculate the margin of error. You'll notice here it's called EBP, error bound for the proportion. And that's Z alpha over 2 times the square root of P prime, Q prime over N. Once you've found the EBP, you're going to use it to construct the confidence interval in the same way that you did for the mean. So sample proportion minus the error bound, and then sample proportion plus the error bound to get your lower and upper bound for the interval. Just like before, once you've got those numbers, you need to interpret them in terms of the context of the problem. So explain what that confidence interval means in terms of the population proportion you're trying to estimate. With a calculator, we're going to see something very similar to the other confidence interval. So for 84 stat test, you're going to have to scroll down a little farther. You're looking for one prop z int. So we are doing a z interval for a single proportion. You're going to enter the information given in the problem. You will notice that the TI-84 is going to ask you for x and n. GeoGebra is going to ask you for p prime and n. So pay close attention for what you're being asked for. Once you've entered all that information, you're going to select calculate and press enter, and it'll spit out the ordered pair that represents lower and upper bound for your confidence interval. For GeoGebra, you're going to use the z proportion estimate command. The z proportion estimate needs 3 pieces of information. It wants p prime, so it wants that sample proportion, the center of its confidence interval. It wants the sample size n, and then it wants your confidence level. Remember that we know that p prime is equal to x over n. So if you're given x and n, you can calculate p prime by dividing. Or if I solve this equation for x, I know that x is going to be p prime times n. If you are on TI-84 and you're in a problem where you're given p prime and n and you have to go back and calculate x for the calculator, you may end up with a decimal answer. You need to round this to the nearest whole number. If you do not, the TI-84 is going to throw an error at you. Because x represents the number of objects in the sample that have a specific characteristic. You can't have part of an object, right? If we're talking about people in a sample that have blue eyes, it's 5 people or 6 people, not 5.5 people. So you need to round this to the nearest whole number before you enter it in your calculator. P prime is always a decimal. So P prime is fine as a decimal. You can do X divided by N. You can also, if you are in GeoGebra and feeding it P prime, you can type X divided by N, whatever your X and N are, and GeoGebra will do that division for you and give you a more exact answer. So you can plug in that fraction instead of the decimal if you want. Okay, so let's do 2 examples so we can get some practice. So example 8.11 says, for a class project, a political science student at a large university wants to estimate the percent of students who are registered voters. He surveys 500 students and finds that 300 are registered voters. Compute a 90% confidence interval for the true percent of students who are registered voters and interpret the confidence interval. So first thing, what are we looking for? Confidence interval for the true percent. And we know that proportions are percentages or probabilities. So they say true percent, they're actually asking for a true proportion, not proportion, proportion. Can't spell today, sorry. So this is an interval for a proportion. Next, let's pick through what we're given. So he surveys 500 students. So that must be our sample size, and finds that 300 are registered voters. And we know that that's what he's interested in, percent of students who are registered voters. So that's the number of successes out of those N trials. 500 people, 300 registered voters. And then we're given our confidence level of 90%. So let's go ahead and do that check before we start plugging things in calculators. So we know that P prime is X over N, which is 300 over 500, which I'm pretty sure is 60%, 0.6. Somebody should check my math, but I'm pretty sure that works out. And that means that Q prime, which is 1 minus P prime, is going to be 40% or 0.4. So we want to check, is P prime times N greater than or equal to 5? So P prime is 0.6, N is 500. We're going to plug that in our calculator. We need to do the same thing with Q prime. Whoops, sorry. Is Q prime times N greater than or equal to 5? So we're going to check that in our calculator, 0.4 times 500. So we grab our calculator, we check. So 0.6 times 500 is 300. That's great. 0.4 times 500 is 200. So our sample is more than large enough for us to be comfortable using a standard normal approximation for a binomial distribution. We're happy campers. So let's go ahead and move on to the actual confidence interval. Clear some space out here. We're going to pull back up our calculator, and we want 1 prop z int. So stats, tests, we want option A, 1 prop z int. And then it asks us for number of successes, 300. Sample size is 500. Confidence level is 0.9. And you can see that it's going to spit out that p prime. It calls it p hat. So it spits out that sample proportion that we calculated and our sample size, and it tells us our interval is 0.564 to 0.636. So our last step is let's interpret that in terms of this problem. So we were trying to estimate the true percent of students who are registered voters. So we can say with 90% confidence that between 56.4% and 63.6% of students are registered voters. I'm hoping that process feels familiar. It's just that added check at the beginning that kind of throws a wrench in the system. But once you've done that check and it's passed, these are both greater than or equal to 5, it's identify the numbers from the problem, plug them in a calculator. Let's try another example, and this time we'll do GeoGebra so we can see what that looks like in GeoGebra. So this example says a survey of 6,000 adults found that 58% say that they would take a ride in a fully self-driving car. Find the 90% confidence interval of the true proportion who said that they would take a ride in a self-driving car. So for this problem, confidence interval for a proportion. So right off the bat, we know we're doing a CI for a proportion. If we pick through the problem, survey of 6,000 adults, that's my N, found that 58% would take a ride in a self-driving car. So they're giving me my P prime and telling me that it's 0.58. And it says find the 90% confidence interval. So they've given us a CL of 90%. So first we do that check, N times P prime and N times Q prime. So N is going to be 6,000. And then P prime is 0.58. I know Q prime is the complement, so 0.42. And then we check if that's greater than or equal to 5. And I said I was using GeoGebra this time. So let's pull GeoGebra up and shrinky this down a little bit so I can get this working. Go. So 6,000 times 0.58 is much bigger than we need it to be. That's 3,480, which is greater than or equal to 5. And then we're going to do the same thing for Q prime times N. So 6,000 times 0.42, and that's 2,520, which is also significantly bigger than 5. So we are cleared to start our confidence interval. I'm going to jot down that information we can't see. We know P prime is 0.58, and we know that our confidence level is 90%, so 0.90. And then we know our sample size is 6,000. So we are doing, let's see, I forgot one proportion. Oh my gosh, I have forgotten what that function call is. Let's go back and check. Mr. Java has a brain fart. The proportion estimate. There we go. Let me start typing the proportion estimate. And the calculator reminds us we want, what do we want? Let's check. What is it asking for again? Sample proportion, sample size. So P prime N and confidence level. P prime N and confidence level. So P prime is 0.58. Sample size is 6,000. Confidence level is 0.90. And it spits out our confidence level. So our confidence level is 0.569. Oh, ooh, if I round that to 3, that's going to be 70 to 0.59. So let's go ahead and look at what that says in terms of our problem. So we surveyed adults, and they're asking us about the true proportion who would ride in a self-driving car. So we can say with 90% confidence that the true proportion of adults that would take a ride in a self-driving car is between 57 and 59%. Okay, one more thing to talk about. Just like for situations where we're estimating the mean, we can use that margin of error to figure out the sample size we need. So if we know the margin of error we want, we can use that formula for the EBP to figure out the required sample size. And we do it the same way. We take that EBP equation, the equation for the margin of error, and we solve it for n. So we have to square to undo that square root. We have to multiply both sides by n, divide both sides by that EBP, and we end up getting z alpha over 2 squared times p prime times q prime divided by that error bound squared. So let's go ahead and use that formula to calculate the sample size in an example. Just like for the mean, before we move on, if n is a decimal rounded up, we know that we can't have a sample size that's fractional values. Okay, so our example says, suppose a mobile phone company wants to determine the current percentage of customers age 50 plus who use text messaging on their cell phone. How many customers age 50 plus should the company survey in order to be 90% confident that the estimated proportion is within 3 percentage points of the true population proportion of customers age 50 plus who use text messaging on their phone? Whew. So scanning that problem on the first pass, I see how many customers should they survey. So they are asking me, what is the sample size? This is not a question about confidence intervals. It's a question about how big does my sample need to be. Then we start picking out what else they gave us. It tells us in that first sentence, determine the current percentage. I know percentage is another word for proportion. So I'm probably going to need that sample size for proportion formula. Z alpha over 2 squared times p prime times q prime over the error bound squared. I know that I want to be 90% confident, and that's what's going to help me find that z alpha over 2. And then it says that the estimated proportion is within 3 percentage points. That's my EBP. So let's go ahead and sort out some information that we have. I just had a total brain fart. Okay, so you'll notice when we go to use this formula, n equals z alpha over 2 squared times p prime times q prime over the error bound, we have one of those values. They gave us the error bound, 3 percentage points, 0.03. Z alpha over 2 is something we can look up really quickly. So let's go ahead and start with those two pieces of information that we have. So we're going to grab either GeoGebra or TI-84 or table E, and we're going to look up inverse norm, assuming I can work my calculator appropriately, 7 bars, inverse norm, enter. And then we want area. We know that it's a 90% confidence level. So 1 minus 0.9 is 0.1. Cut that in half, I'm going to get 0.05 in each tail. So my Z alpha over 2 is going to be 1.64. And then on the bottom, I know that my error bound is 3 percentage points, which is 0.03. And then we run into an issue with P prime and Q prime, where you will notice that's not given to us in the problem, right? If we reread that, suppose a mobile phone company wants to determine the current percentage of customers who use text messaging on their phones. They give us a confidence level. They don't give us any other information. So in cases like this, where you're estimating a sample size and they don't give you P prime and Q prime, we want to choose the biggest possible combination. We want to be as certain as possible that our sample size is large enough. And that happens when both P prime and Q prime are 0.5. There's a 50-50 chance that you get a success or not. So when P prime and Q prime are missing, assume that P prime and Q prime are 0.5. From here, this is something we can check easily on our calculator. So we're going to pull back up our TI-84s, and we're just going to plug and chug that formula. Let me clear up some room here. So we have 1.64 squared times 0.5 times 0.5 divided by 0.03 squared. We hit enter and we get 747.111111. So n equals 747.1. And remember that we always round up. I can't have 0.1 of a person. So we're going to use 748. So if we want to ensure that we've got a margin of error that's about 3%, that means that we need to use a sample size of 748 people to ensure that we can be 90% confident that we're within that 3% rate. Okay, that's it for the week 4 videos. This week we are only focused on confidence intervals. If you have questions, drop by office hours or send me an email or text message. Otherwise, I'll see you on the discussion forums and in the videos for next week.